Hello, my name is Gregory West, and I'm an associate professor at the University of Montreal. And thank you for attending my talk today. Okay, so the talk is called The Relationship Between Video Game Playing, Memory, and Reward. And so we're really going to be exploring these three topics today and the relationship between them. So first of all, I'd just like to start off by just acknowledging two of my research collaborators who are implicated in a number of the studies I'm going to talk about near the end, Veronique Bobat and Caroline Fitzpatrick. And also, I want to just mention to everyone that I do not have anything to disclose in terms of conflicts of interest. I've never accepted any money from any video game companies to conduct the research that I'm going to talk about today. So I want to start a long time ago at the beginning really of our history because the fact that a new technology emerges and has an impact on our cognition or our brain is really not a new phenomenon. This has been happening really since humans moved into cities at the dawn of agriculture. And so research suggests that our hunter-gatherer ancestors, this is before we moved into cities, before the era of agriculture, really had a lot of cognitive abilities and even some that we really don't use anymore today. For example, hunter-gatherers had a very acute sense of taste and smell, it is theorized, and many cognitive processes were needed to survive. So in these kinds of environments, a person would have to really master a number of skills and competencies in order to survive and contribute to their community. This changed when we moved into cities, however, and people were able to more specialize their skills, but at the same time, they didn't now need to master many skills to survive, because now when people move into cities, this is now almost 7,000 to 12,000 years ago, as it's indicated on this slide. When this happened, people were able to rely on other people's specialized skills while having their own, but didn't have to, like I said, master all skills needed to survive. And so when this happened, and this is what I'm showing here on the graph, there was a consequence to the nervous system, and specifically the size of our brains. And there was actually a reduction in brain size that occurred as we moved away from the hunter-gatherer period into this period that included the development of agriculture, moving into larger communities and eventually cities, and even occurring while we developed a language only about 50,000 to 150,000 years ago. So there are many different hypotheses as to why this occurred, but one is that as a result of hunter-gatherers no longer needing to master so many different complex skills, as a result, less brain tissue was needed, because now we can rely more on each other, on our neighbors, to rely on their expertise where we have our own specific expertise. And as a result, cranial capacity, as it's shown here, decreased. So this is maybe one early example of how technological advances here, the advent of agriculture and all the advances that came with it, may have impacted our nervous system. Fast forward to many years later, and then humans began to create more and more what are called intellectual technologies. So basically, these kinds of technologies, this specific category, are tools that people can use to do something that would have otherwise had to been done with our own brains, right? So something like a calculator, right? Doing a mathematical calculation, instead of using our brain to do that, we can just quickly use a calculator to do this. And the abacus was the first iteration of that kind of technology. Even typewriters and printing presses, as we'll talk about in the next slide, is a type of intellectual technology, because now we can store information outside our memory on a piece of paper really easily, mass produce it, share it with others, and then that's less that we need to remember in our own minds. So again, it's an intellectual technology. And even something like a map can be considered an intellectual technology as well. And we'll be talking a lot about maps today. So a map is used to find a location, to navigate to a location in a city, in a countryside. It can be used in many different contexts. But when a map directs you to go to a certain location, especially if you've already visited that location, you're using the map to return to a location instead of using your own memory, your own spatial memory to return to that location. And so it's an intellectual technology because now the map is doing at least some of the mental work for you instead of you just using your brain to get to that location. And now we have far more advanced versions of maps called GPS systems that are on everyone's phone now. And now more and more people are using devices and digital maps in the form of GPS to navigate to locations that they could have otherwise remembered to return to using their own brain. So again, it's an intellectual technology. They help us, and we will explore this idea in more detail later in the talk. And now fast forward to the internet age, the smartphone era we're in. Everyone now has a computer in their pocket. They can now easily access information at any given moment, anything that humanity has ever discovered. But even this change in how we engage with information, from reading books to searching for something on the internet, has been shown to impact, in this case, our brain. In this case, the activity in our brain when we are treating information displayed on a screen versus in a book. And so this was one of the earlier studies that examined this topic, and they asked participants while they're in an fMRI scanner to either read a normal text like they would find in a book, or read, in the second condition, the same text, or I should really say research the same text, but this would be done through a series of hyperlinks, like on a typical website. And so here on the right, this is what we call a contrast in fMRI activity. And what we see are the areas of the brain that are more active in the quote unquote internet condition versus the standard reading condition. And so, yes, there's more activity in the brain when people have to research a topic using the internet versus just reading a book. But that is not necessarily a good thing. And so these regions are actually involved in decision making, and also inhibiting distracting information. And so the idea here is that reading when done, or researching a topic when done on the internet, is actually more shallow as a result of the fact that your brain constantly is being interrupted from every jump from one link to the next. There has to be judgments made whenever a link is followed, whether or not it's relevant to the topic, whether to return and find another link. And so this constant switching interrupts the brain from more deeply reading the text and understanding the text that the person is engaging with. So that was just to show you that the fact that a new technology shows up in people's lives and changes our cognition and even our brains, we'll see later, is really not something new. So what we're going to be discussing today is really the impact of video games on the reward system and also on spatial memory performance. And so we really focus in our lab on spatial memory because it is a good estimate of the health of a structure in the brain that is very important for healthy cognition from when we're young to when we are old adults. And that structure is called the hippocampus. So the hippocampus supports spatial memory, memorizing um, the relationship between objects in an environment, remembering how to return to previous locations, and so forth. And so here, to start off this topic, which is going to tie in a little bit to what I was talking about before, I'm going to talk about a study that used a mobile video game to measure spatial memory performance uh, from over 2.5 million participants worldwide. It's a very high sample size. And so this game was free to download on people's cell phones. They were asked to play the game. They were told that it was for research purposes. Of course, they were aware of this. And what they really completed in the game was what we would call a typical wayfinding task. So here, this is a typical level that participants would play in the game. It was called Sea Hero Quest. And the goal was to navigate this little boat in a number of environments. And the environments would have different landmarks, different pathways. So we can see here there's a volcano, there's a mountain that they turned around and rotated. They would see different landmarks, maybe a lighthouse or a building. And their goal was simply to first memorize using an overhead map, a more traditional map, where a number of target locations were. So here, the target locations are indicated by these flags. And so in this case, the player would have to memorize the locations of these four flags. And then they would simply, when in the first person view here in the level, after they encoded these locations, they would have to simply visit the four locations. And here we could see a representation of many different participants completing the same level. And the more white the area is on the map, that means more people took that exact path. And then you can see there's deviations from those main paths that people took. So that's the variability amongst participants. And so basically, if a participant really went directly to the four locations without deviating too much, they were said to have a better spatial memory performance. They took a more accurate path to the four locations that they needed to visit. And so through this behavioral measure, these researchers who are our colleagues at the University of College London were able to estimate people's spatial memory ability using this game. And here's just another example of another level from this same game. And we can see here now individual pathways that individual participants took. And you can see, let's label this one. You can see this participant took a very efficient pathway, so didn't deviate too much at all. And then this final one down here, you can see there's a lot more deviation. This participant basically was less efficient at visiting the four target locations. And so we would say that this participant number one versus number 9 here would have better spatial memory performance, which is indicative of a more healthy or functional, let's say, hippocampus. Again, that structure that supports this very cognitive ability. And so now to kind of return to what I was talking about at the start of the talk was the impact of technology, or here we can say more so the impact of modernization and its impact on cognition, brain and cognition. And so here, using data from that very mobile video game, they were able to show that worldwide, if someone grew up in a city, they would have less efficient spatial memory performance compared to someone of the same age and gender who grew up in a more rural area. So this uh, figure has a lot to show. So first of all, let me just point out a couple of the key things. So we know spatial memory ability in general declines with age. So we have age here on the x-axis. So we have 20 to 70-year-olds. And so we could see that spatial memory performance, as estimated by IFCEO Quest, declines with age. There's also a known gender difference. Males outperform females typically on a test like this. There are reasons for this that we can talk about another time. But the main thing that I want to highlight here is if someone grew up in a city, they had poor spatial memory ability regardless of their age or gender. So that's the difference between the two lines that I'm pointing out right here. So already I can again start to see that modernization could actually have an impact on brain and cognition. And here's a more detailed look at this. So the question that the authors here want to answer was, why was this the case? And so it was hypothesized that newer cities, so cities that developed later in our history, like the ones, for example, in North America compared to the ones that developed in Europe, newer cities are laid out in a way that are less complex, less random. And here we see an example of two cities. So one on the bottom here is Chicago, so a more modern city compared to Prague in the Czech Republic. And so we see that the city of Chicago is more like a grid, right? Just a series of streets aligned in parallel and perpendicular from each other. And so to navigate and find your way in Chicago is going to be a lot more easy than navigating and finding your way through the city of Prague, which has a lot more turns. And really, the term here used is entropy. So there's more entropy in Prague. We can think of entropy simply put as being more random. So there's more randomness to the way all the streets connect and deviate from each other in Prague compared to Chicago. And so what's here on the right shows that this actually can partly explain the difference in growing up in a city or growing up in a more rural area, because if there's a lot of randomness in the city that you grew up in, then there wasn't actually a difference between you and someone who grew up in a more rural area if you grew up in a city like the Czech Republic. So that's what we see here in this graph. So this is basically an estimation of the effect of the difference between growing up in a city or in a rural area. So we have Czech Republic right here, and then we have the United States, which of course includes Toronto right here. There's Canada for the record. And so these newer cities really do produce citizens with poor spatial memory performance compared to these older cities, which again are more difficult to navigate through and as a result are more engaging to the brain in terms of learning a new environment. And we'll talk in more detail in a few slides about why that might be the case. But again, This is again an example of how modernization, technological advancements can have an impact on brain and cognition. This is nothing new. And then this is another study by another group, but really looking at the same topic. And here the researchers compared adolescents who either grew up in a rural setting or in a city. And here we have an effect in the structure that I was talking about previously, the hippocampus. Here we see that adolescents who were raised exclusively in a rural area, in fact, have more gray matter in the structure that I was talking about, the hippocampus, which again is the same structure that supports spatial memory ability, like was measured in CIFEO Quest, that mobile video game. And gray matter means basically a part of the tissue that includes the cell body of the neurons. So it's a type of tissue in the brain, and more gray matter in an area of the brain is usually almost always associated with it being used more often. And when gray matter is lost in a certain area of the brain, cognitive functions that that very area supports will actually suffer. So people will lose cognitive ability in that domain if that part of the brain experiences gray matter loss. And here we see that the same effect was replicated in the behavior. So the researchers here gave participants a spatial memory task, again, one that would rely on the hippocampus, and people who grew up in a more rural area who had more gray matter in the hippocampus also displayed better cognitive performance on that task as well. And so now let's talk about what people are doing when they use their hippocampus to navigate in a new environment. And so we can measure this kind of process using a similar task that the CIFEO Quest game used, but in the lab, we would call it a virtual wayfinding task. So wayfinding is basically estimating people's ability to navigate, find locations that they previously visited in a new environment. And in the lab, we would use a similar task where we put someone, for example, in a small town. We would ask people to visit a number of landmarks. Again, this is very similar to the CIFEO Quest game that I previously showed you. And so let's imagine that they would have to first visit a store, then the bank, then there might be a bus stop right here, like some of the locations featured here in the picture. And then after they have gone to all the target locations, then we would ask the participants to return to a certain location. So let's say they're at the bus stop over here, and then we ask them to return to the store. Well, someone who has better spatial memory performance will remember the relative location of the store from the bus stop where they're currently at, and take a very straight, efficient pathway back to the store, okay? So this person really learned the relationship between the store and the bus stop. In contrast, if someone had poor spatial memory performance, they wouldn't necessarily efficiently learn the relationship between all the target locations that they were asked to previously visit. So someone who had a poor spatial memory ability might actually turn the wrong way first, maybe get a little lost, end up over here and take a long, basically meandering path until they eventually remember the location and return to the location that they were supposed to go to. And so here, behaviorally, we can measure people's spatial memory ability through this kind of virtual wayfinding task. and we can estimate people's integrity of their hippocampus, the health of their hippocampus this way as well. And when people perform well in this kind of task, they develop what is called a cognitive map. And a cognitive map, I already mentioned learning the relationship between objects or landmarks in the environment. And when people do that, they're forming that cognitive map. And what it is an eternal representation of the environment, but not in not in one of those intellectual technologies like a brain, like a GPS or a map, but they're in fact using their brain to store that information, form that cognitive map, and when that happens, the hippocampus is recruited and relied upon. So as I showed previously with the C-Hero Quest data, wayfinding performance declines with age. So cognitive abilities that rely on the hippocampus decline with age. So here we see that errors in that wayfinding task I just showed you are greater in older adults, people over 65, compared to younger adults, people in their 20s. And we could see when we just look at older adults, people about 60 to 80, that with age, more errors are made, indicative of basically that hippocampus, its integrity, its health is declining with age. Okay, so we can use a wayfinding task to estimate people's spatial memory ability and as a result, the health of their hippocampus. But how can we tell if a participant who comes to the lab is using their hippocampus or not to memorize where to go in a new environment? So we call this navigation. So when someone's navigating in a new environment, how can we tell if they're using their hippocampus or not? And so it turns out there is a way to determine this, and it's going to be an important part of understanding the results related to video games, which I will get to, I promise, in a few slides. And so I thought it would be important to really explain the tasks that we use in the lab to determine if someone's using their hippocampus or another part of their brain to memorize new locations in a new environment. And it turns out this maze that we can give participants virtually was developed by researchers before it was done in humans. It was done with rodents. And so this virtual task that I'm about to show you is really an analog of mazes that were developed for rodents. Okay, so here is the task that we use. It's actually called the 4 and 8 virtual maze, and this is because there are 8 arms to the maze. And in part 1, the arms that are open consist of 4 arms, and the arms that are closed also consist of 4 arms. And so there are 8 in total, 4 are open, 4 on a virtual maze. And here the participant simply has to visit the end of the 4 open arms and collect an object and return to the center of the maze. And so what the participant will have to do in the second part is they're going to have to memorize which of the arms were open and which of the arms were closed in order to complete the task properly. And I'm just going to pause it here. And now you probably will notice that there are landmarks. Some are close, some are far. So we see a tree that's behind us. There's a rock here. There's some mountains more further away, different colors. And so these are kind of like the landmarks that I was talking about when I was talking about the wayfinding task. that we also ask in our lab participants to complete. And so the participant could have the choice to learn and remember the locations of these landmarks and the relationship between them, just like someone who is really good at the wayfinding task or the Sea Hero Quest game would do to efficiently return to previously visited locations. So returning to explaining this task, the participant would eventually collect all 4 objects, and then we would start the next part of the task where all the arms are open. And like I said, the participant will have to remember which arms were open, which arms were closed by visiting only the arms that were closed during this first part that I'm showing you right now. Okay, so I don't have a lot of time to explain exactly how we determine who uses their hippocampus and who doesn't to complete this task. But simply put, if people tend to use the landmarks that I just described, those people tend to be using their hippocampus. And if they don't, then they're using another part of their brain that is actually part of the reward system, and it's called the caudate nucleus. And so we call people who complete this task using their hippocampus, we call them spatial learners because they use a spatial strategy to complete the task. And in contrast, people who use their reward system, their caudate nucleus, we call them response learners. So I'll be using the term spatial learner, response learner, spatial strategy, response strategy. Just know when I say spatial, it means hippocampus dependent strategy. And when I say response, it's a caudate nucleus or reward system dependent strategy. So here are results from people who completed the 4 and 8 virtual maze, either by using a response strategy or a spatial strategy. And on the left here, I just wanted to show you that the proportion of people that adopt a spatial strategy versus a response strategy to complete the maze changes over the lifespan. So when we look at children, these are children under 10 years of age, we see that the vast majority of children are spatial learners. So they're using their hippocampus to learn new environments. When we get to middle age in our 20s, now only about 50% of us, it's about a 50-50 split typically, that are using their hippocampus to learn a new environment that they encounter. And then, as I was saying, then people shift away from using their hippocampus towards using their caudate nucleus when they are presented in a new environment. And that's why now we see the majority of older adults, these are people 65 and older, are now using their caudate nucleus and not their hippocampus when they have to learn that new environment. Now, importantly, if we scan the brains of these people who complete the 4 and 8 virtual maze using a spatial strategy and a response strategy, when we compare them, we can actually see differences in the gray matter. That's the number or the amount of tissue in that structure. And what we see is that people who use a spatial strategy have more gray matter in the hippocampus compared to response learners. We can say spatial learners, response learners, because it's a kind of learning task. So spatial learners show more gray matter in the hippocampus compared to response learners. And when we look at where response learners display more gray matter, we see that they display more gray matter in the caudate nucleus. So the way someone solves the maze indicates if they have more gray matter in the hippocampus or in the caudate nucleus. And another way we can look at this is here we can actually say that response learners actually have less gray matter in the hippocampus. And so that point will become important in a moment. Here, I also want to show that the amount of gray matter in humans and in mice between these two structures share typically an inverse relationship. So someone who has more gray matter in the hippocampus will have less gray matter in the caudate nucleus. And also the reverse is true. Someone that has more gray matter in the caudate nucleus will have less gray matter in the hippocampus. And so this is to highlight that these two systems, when we're healthy, operate together, but there is a competitive nature between these two systems. And if someone tends to use one more than the other will experience gray matter loss, and that can have an impact on cognitive ability. Now, before we start to talk about video games, I also wanted to highlight why we care about the amount of gray matter in the hippocampus, the health, the integrity of the hippocampus. And it is because across the lifespan, when we have less gray matter in the hippocampus, it puts us at risk for numerous neuropsychiatric disorders. So it is known that people when we're younger, earlier in life, people with less gray matter in the hippocampus are more prone to develop depression. They're more prone to develop PTSD in the face of a stressful event. They're more prone to develop schizophrenia. And when we're older, people with less gray matter in the hippocampus have a higher risk of developing dementia, including Alzheimer's disease. So what this means is that we should be very motivated throughout our life to keep our hippocampus and indeed our whole brain, but especially the hippocampus healthy. And so if we're doing things in our day-to-day lives that are having a negative impact on the hippocampus, the idea here is that that could possibly put us at risk for developing certain neuropsychiatric disorders. And so we should avoid that. Okay, so now finally, with all that background information, I thought was important for you to have to really understand what I'm about to talk about in relation to video games. It's important also to understand, though, that I'm going to be talking about different types of video games, different genres of video games. And as you can imagine, these different types of video games will ask the players to do very different things. And as a result, will have a different impact on brain and cognition. So when we use the term video game, we have to be probably a little bit more specific and talk about what type of video game is having a certain impact. Is it an action game, like a first-person shooting game? Or is it one of these 3D platform games like Super Mario 64? Or is it a logic puzzle game like Tetris? All these types of games will have a very different impact on brain and cognition, as we will see. So let's talk now about how video games impact certain parts of the brain. And yes, we're going to be talking about the caudate nucleus and the hippocampus, because it turns out research has shown that the different games can impact these structures. And so I told you that the caudate nucleus is a part of the reward circuit. And here is some evidence for that right here. On the right, participants, these are adolescents, and they were scanned in an fMRI scanner while completing a gambling task. So it's a task that asks people to select cards, and they can win certain amounts of money and lose certain amounts of money and take higher or lower risks. So it's really a measure of risk taking. And people who played more video games per week, so this is hours per week now, had more activity in the caudate nucleus than people who played fewer hours of video games. So this structure involved in the reward circuit. It's also involved in assessing risks. It is more active in people who play video games. Also, this same study showed that people who played video games more frequently, adolescents, they had more gray matter in this very same structure as well. And this study did not, in this particular analysis, look at different types of video games. These are video games all mixed together. So it's a little bit difficult to determine if this effect is being driven specifically by action video games or maybe a different type of video game. But this was really one of the first studies to show that video games can have a significant impact on the brain. So it was an important finding nonetheless. This study was done in the 90s, and they had people play a very simple video game, almost like a Space Invaders style simple game. And they measured the amount of dopamine, which is a neurotransmitter intimately involved with reward, in two structures in the reward circuit, the caudate nucleus that we've talked about already, but also the nucleus accumbens. And what they found was when people were playing this video game, that dopamine, the amount of dopamine released during this video game playing was quite significant and similar to the amount of dopamine that would be released when someone took amphetamine, which is, of course, an addictive drug. So this is evidence even from way back in 1998 showing that even a simple video game can really engage these reward structures in a significant way. So based on this previous data, we had the hypothesis that people who specifically play action video games, and I will discuss why we chose action video games in a moment, but this study we conducted on people who played action video games, and we compared them to people who do not play action video games. So they were our control condition. So that's what we see here on this graph. We have non-VGPs, video game players, versus action VGPs, or video game players. And so what we did was we had everyone simply complete the 4 and 8 virtual maze. So I discussed this with you in detail. So we know that people can either solve the maze by using a spatial strategy or a response strategy. And because we already knew that video game playing was associated with more dopaminergic activity in the reward system and also more gray matter in the system, and specifically in the caudate nucleus, we hypothesized that people who habitually played action video games, this is in this study was about 10 hours a week or more, would more often solve the 4 and 8 virtual maze using a response strategy compared to non-video game players, people who didn't play video games. And so what do we see here? We see that our non-video game players were actually a bit more biased towards using that hippocampus dependent spatial strategy. But, you know, it was around 50-50, what we see in a typical young adult population. These were young adults in their 20s. But look at here, we see that our response learners the majority of them were video game players. So another way to say it is the majority, 81% of the video game players, the action video game players, indeed solved the maze using a caudate nucleus dependent response strategy. And we chose action video games because up until this time, the majority of the positive effects relate to visual attention and motor control and mental rotation that I had previously showed you briefly, investigated specifically action video game players. So we wanted to use really the same sample used in previous studies by previous researchers. So that's what we found. We also took the participants that participated in this study and asked them to go in the MRI scanner, and we scanned their brains. And as predicted, we found that our action video game players who used a response strategy, overwhelmingly 81%. And remember, if we scan the brains of response learners, what should we observe typically? We should typically observe less gray matter in the hippocampus. And so that's what we found here. These action video game players, 10 hours a week or more, displayed less gray matter in the hippocampus. So this is interesting. So our initial hypothesis was supported, but it's important to point out that at this point, the data is correlational in nature. So what does that mean? So you may have heard the term correlation does not mean causation. And so it could be the case that there's a relationship between video game playing and gray matter in the hippocampus, but it doesn't necessarily mean that video games caused this reduction in gray matter in the hippocampus. So to determine that, we need a more complex experimental design. And so luckily, we were able to conduct such a study, but also other researchers uh, before us conducted such a study as well to determine a causal relationship between video game consumption, playing video games, and direct changes in brain structure. And so this group in Germany, led by Simone Kuhn, trained participants at home for about 50 hours. It was a bit variable, participant by participant, but it was around 50 hours of training. And they asked people to play the 3D platform game Super Mario 64 at home. Now, this game was chosen because it asked participants to learn new environments. And we know when we learn new environments, we form that cognitive map that I was talking about, which recruits the hippocampus. So the hypothesis was that as participants progress through the different levels of this game to accomplish the task, they would have to return to locations they previously returned to. And I'll note that there's no GPS in this game. A lot of video games have GPS in them. And as I briefly explained, if we're using our GPS, we're not using our brains. So this type of game actually asks people to use their brain to learn the new environments, learn the relationship between objects in the environment, landmarks in the environment, and that should recruit the hippocampus. And so here is the change in the hippocampus between the time before the training and the time after the training. So this study followed participants longitudinally, and they were able to see a change that they could determine was a result of playing the video game. So now we can infer some degree of causality that playing this game, Mario 64, caused an increase in the hippocampus, increased gray matter in the hippocampus. Now to continue on with the study that we did in my lab. And so we asked people to now come into the lab over a period of 10 to 12 weeks and play either a series of action video games like Call of Duty, first-person shooting games on a PS3, or play a series of 3D platform games, which began with Super Mario 64 that I just described. So participants trained for the same amount of time in each group, 90 hours over a period of 10 to 12 weeks. We were able to scan the participants' brains in the MRI before and after. And again, just like the study that I described previously, we were able to observe any changes that might occur as a result of the training on a particular type of video game. And importantly, we also had people complete the 4-8 virtual maze to determine if they used their hippocampus to complete the maze or their caudate nucleus. And we also showed in this sample that participants who began the study using their hippocampus, this is before they played any video games, if they used a hippocampus-dependent strategy, they had more gray matter in the hippocampus. And if, by contrast, participants used a caudate nucleus-dependent strategy, they had less gray matter in the hippocampus and more gray matter in the caudate nucleus, replicating previous results. So why is this important? So this means that our spatial learners who began either playing 3D shooting games or in the other condition, 3D platform games, spatial learners began that study with more gray matter in their hippocampus. In contrast, response learners, again, same thing that they're being trained on, they started with less gray matter in their hippocampus. So there's this biological difference that these two groups began our study with. And as we'll see, that was important for interpreting the results of the training study. So it turns out that whether or not people were a spatial or response learner was important for determining the impact of these video games on the brain. So here what I'm showing are the changes between time 1 and time 2 before and after the training. And here is what we would call, in statistical terms, an interaction. So what this means simply is that the effect on the hippocampus between time 1 and time 2 was dependent on whether or not someone began our study as a spatial learner with more gray matter in the hippocampus or a response learner with less gray matter in their hippocampus. And so we see here, this is just where the site of the effect was in the hippocampus. Here's another view. And so people, and I should also point out, these are action video games. This was the 3D shooting video game condition. People who are spatial learners actually increase their gray matter in this important structure. But unfortunately, people who already began with less gray matter in the hippocampus, or response learners, actually saw a further reduction in their hippocampal gray matter. And remember, these were healthy young adults, and about 50% of young adults will use a response strategy to learn a new environment. So about 50% who are regularly consuming these types of action video games could indeed be reducing their hippocampal gray matter. So if you remember the importance of the hippocampus and what reduced gray matter in the hippocampus is associated with, this is not a very good thing to do to your hippocampus. These are the results now for the 3D platform game. And so I think it's important to point out here that these participants, we had spatial and response learners complete this training condition. These participants came to the lab the same amount of time. They were in front of screens playing video games for the same amount of time, the same 90 hours. And we use these really as our control condition. So everyone got between the two training groups the same treatment. But here, what we observed are only positive effects on the brain as a result of training on 3D platform games like Super Mario 64. And so here we see in our response learners, these are people that began our study with less gray matter in the hippocampus. They actually grew gray matter in the hippocampus, as indicated right here in this site of that structure. Now our spatial learners, remember, they already had more gray matter in the hippocampus compared to the response learners. So they didn't experience gray matter growth in this structure. Instead, we observed significant gray matter growth in a neighboring structure called the entorhinal cortex, EC, right here. And so I mentioned the importance of the hippocampus for cognitive health. Well, it turns out the entorhinal cortex is also very important for cognitive health. And is really intimately involved with the hippocampus. So when I was talking about how the hippocampus supports spatial memory, navigation, the entorhinal cortex is intimately involved in supporting that type of behavior as well. And it turns out also that more gray matter in the entorhinal cortex predicts healthy cognition across the lifespan. So the fact that in these spatial learners who have more gray matter in the hippocampus, the fact that they also experienced gray matter growth And another important structure in this memory system is a positive finding. So again, to repeat, the same amount of time in front of a screen, but it was really the content of the screen, the type of content of the screen that determined um, the impact on the brain. And now I'm going to finalize the talk with a other study that we recently did. We examined data from the Quebec longitudinal study of child development, and we're interested in the relationship between video game playing in adolescence and symptoms of attention deficit hyperactivity disorder. And so why were we interested in this? So first of all, as I already explained, we know that people play a lot of at least action video games have an engagement in their reward circuit that is more so than people who don't. And specifically when we're talking about that structure called the caudate nucleus that we have been discussing, that structure is also implicated in certain symptoms related to ADHD as well. It's implicated in impulsivity and hyperactivity. And so that kind of evidence at least allowed us to create the hypothesis that there might be a link between consuming video games and the development of symptoms related to ADHD. Also, previously, it has been shown that children who play a lot of video games also are more likely to display symptoms of ADHD. But like I said, that is an association, a correlation. And so what we're able to do here is by collaborating with the folks who run this study, is that we were able to use data that followed these 13-year-olds until they were 15 longitudinally. And we were able to examine data about their video game playing habits at age 13 and see if the amount of hours per week of video games that they played at age 13 could predict the development of symptoms related to ADHD. And here specifically, it was symptoms of hyperactivity and inattention, both associated with ADHD. And so what we're able to find is that higher video game frequency at 13 predicted increased symptoms of hyperactivity and inattention at age 15. And so what does this mean? So first of all, I think it should be appreciated that to really establish a true causal relationship between something like video game playing and symptoms of ADHD in children and adolescents is more difficult to do for the reason that it wouldn't be ever ethical for very good reasons to randomize 13-year-olds to a group that could potentially be related to them developing symptoms of ADHD, and then a control group for the other group of participants. So as a result, this is almost like the highest type of quality data that we can obtain to establish a causal relationship between these kinds of variables. And so because of the fact that these participants were followed longitudinally over time, and the relationship between the variables appeared in the way that I described them. Increased video game consumption at 13 was related to the development of these symptoms of ADHD. It's pretty convincing evidence that there is a significant relationship between video games and this type of symptomology. Now, I should mention that unfortunately, we did not have data about the specific type of video games that were being played by these participants. And so these data cannot speak specifically to whether or not symptoms of inattention and hyperactivity are caused by playing action video games. But I would point out that based on the other studies that I did show you today, that because it is known that these types action video games specifically engage the reward system, it is a likely hypothesis that this effect that I'm showing you right here is being driven by the consumption of action video games and not games like Super Mario 64 or logic and puzzle games like Tetris. And so with that, thank you for your attention. Thank you to my collaborators listed here that were instrumental in realizing the research from my lab that I was talking about with you today. And thank you to the funding organizations, the public funding organizations that supported my work.